Byung-chae from the Yonsei University. And it's my great pleasure and it was my honor to have this opportunity to explain a new communication paradigm. For this topic, I have the really wonderful students and colleagues here. Especially I have I'd like to thank my students, Bon-hong and Changmin, and they mostly prepared the materials. They helped a lot. So I just want to take the opportunity to thank them first. All right. I have checked the syllabus of this course, and you had quite diverse topics for the next generation communications, from ultra reliable low latency communications and quantum mechanics to the computing. So here, as you were announced, it's time to have the more new contents than ever. So I'm not quite sure how many audiences and students have ever heard about the molecular communications. So anyone here, you guys can turn on the mic or turn on the camera to have the questions or whatever you want.
I think they have to write you. It's not possible for the students, I think, to not for all of them at least, to put on the microphone.
The thing is that if I have the full screen, I cannot see that the public chat information.
Okay. We will contact you when there are questions. Okay.
Right.
So just let you know that this last semester, what we try is to gather the best topics for them, which they might be useful for them in 3 to 5 years, right? So molecular communication is one of them. Quantum is another one. It's a bet in the future, right? So.
All right. Okay. Let's switch back to the full screen mode. So I think not really many students heard about the molecular communication, but it's totally fine. I will explain the step by step. Let's see, what is that? Right, and before starting the lecture, let me take the opportunity to introduce myself. Again, this is Chan Byung-chae, and I am a professor at Yonsei University in Korea. So before joining Yonsei University, I was with the Biolabs in New Jersey in the United States for 2 years. Before that, I was with the Harvard University as a postdoctoral research fellow. I got a PhD from UT Austin under the supervision of the Robert Heath. And I am now I have also several roles for the IEEE. I am now an editor-in-chief of the IEEE Transactions, Molecular, Biological, the multi-scale communications, which deals mainly the molecular communications. You know, when I joined the Yonsei University in 2011, I tried to distinguish myself, by developing a research program in wireless communications with a strong, the real-time prototyping component. One area of focus was on the full duplex wireless communications, where I guess you already heard about the full duplex concept, where the transmitter and the receiver they can use the same spectrum simultaneously. So my group debuted the system on the real-time, the full duplex radios at the IEEE GlobeCom 2014. And later, we developed it and demonstrated more sophisticated full duplex MIMO strategies and reinforcement learning-based flexible MIMO and wireless virtual reality and haptic MIMO and more at the almost every following GlobeCom till 2019. And the last year, we were not able to demonstrate our system, so we skipped our annual demo event. And from the achievements, we got several demo awards. I also try to differentiate myself from the other colleagues, by opening a new research area. I took a risk at that time, seriously, and I developed also the research program in molecular communications. at that time, the concept was that the very is the infancy, and we built up a theory in this new area just by reading and understanding fundamentals in biology and other the area. Because the many thought the molecular communication was crazy. I mean, let alone molecular MIME communications, and we developed it a number of prototypes of this system, including the macro scale, meso scale, and nanoscale diffusion MIME system. So I think I can show you our demo videos. I think the next week in the third course. All right. Here is the outline of my lectures. I was told that I'm given 3 units, like almost a little bit more than 3 hours. So I will try to deliver the key messages with not really many math equations. So the lectures consist of mainly the 4 parts. The fundamentals of the molecular communications, the communication and information theory for also the molecular communications. And we also have the test beds and prototypes to validate the concepts. So in the first part, I will start with quite the famous researchers like the Einstein, Brown, and the many others. In the second part, I'm gonna cover the channel models, the modulation techniques, and the detection algorithms, followed by the channel capacity in part 3. And this is the new communication paradigm. So the seeing is believing. So that's why I try to have the real prototypes. Otherwise, nobody will believe this kind of the system will work in practice. So again, I personally prefer to have the many technical discussion even during my lectures. So I'd like to suggest you leave the as many questions as possible in the chat box, and I will try to have some answers all of your questions. So is there any questions so far? All right, and let's move on to the fundamentals. The figure is quite colorful, right? Our research area has gone through a series of the revolutions with the introduction of new communication media, sometimes from wires to air, and most recently to liquid-based media. So the introduction of such different the communication paradigms has catalyzed the development of novel applications that were previously unthinkable. The most recent of these paradigms is the molecular communications, which facilitates the healthcare applications involving intra-body networking. So by providing a means of the communication through the ubiquitously connected like blood vessel, arteries, veins, and capillaries, the molecular communication-based e-health applications enable a host of new Internet of Nanobio Things services. So here, I just wanna ask a question. Here, is there anyone, maybe, and then any student who can differentiate 6G from 5G? Even 5G is now being well deployed, but I believe there are somewhat limited at killer applications. We will have the more killer application though. So in 6G, it's maybe beyond a 6G. So we're gonna have the quite different applications. This is why I here claim biological the layer on top of OSI's the 7 layers to support the e-health applications. Sometimes we call the RF part, radio frequency RF part, is layer 0. So here we add one more possible approach to layer 0 instead of the RF technologies for different the applications. So to realize the Internet of the Bio-Nano Things in practice, here we have the conceptual some diffusion. The health monitoring scenario we spotlight here employs the nanomachines, which can communicate with each other via molecules, and so that the system can have the better biocompatibility than a system employing the electromagnetic or the RF components. So the machines are capable of adaptively transmitting and receiving the target molecules in vitro the environments with the help of the state-of-the-art nanomachine technology. So here, let's assume to implant 2 tiny nanomachines to the up and down of your heart, and we just sporadically and transmit the signal like 1 0 1 0 1 0 some sequence. So once we detect some abnormal signal sequence, and then those kind of the nanomachines can relay those information to the some machine on the skin, and then we might have some alert message on our smartphone. Oh, you might want to go see a doctor. The heart the information is quite not stable, and that could be one possible applications just by using those kind of the molecular communications. So for these applications, we should first understand the fundamentals of the molecular communications. So I will get back to this slide after the introducing some technical detail. All right, then what is nano communication networks? It interconnects. This is a definition from the some textbook. It interconnects the several nanoscale machines to carry out the complex task in a cooperative manner. There are 2 types of the nano networks. We could still use the electromagnetic based one, but in that case, the carrier frequency would be like a few hundred terahertz or something like that. And I'm not quite sure if we could penetrate any very thin skin just by using those the ultra high spectrum area. And also we can also use the molecular based system. So the IEEE also initiated the standard, the working group in the working group 1906.1 in 2010. But frankly, I haven't seriously followed the activities of the standard. So it seems they have focused on conceptual model and a standard term for the ad hoc network and the communications at the nanoscale. So for the molecular communication, the nanomachine sends, receives information encoded the molecules, as you can see from this slides. One can easily design the system like this. Suppose we have the controllable spray. If I spray for example, perfume, for example, and you can easily smell it, and you can decode this smell into like binary 1. After some time, maybe after 5 seconds or 10 seconds, or sometimes after 1 minute, which indeed this is the related to the simple period. If you don't smell anything, you may think, oh, I sense digit 0. So we can separate two different binary information, 1 or 0. I smell it, it's 1. I don't smell, and it's at 0. So this is a very simple modulation for the molecular communications. We here also compare the differences between the traditional, the electromagnetic communication, and the proposed molecular communication. Obviously we have the totally different carriers. And we do not rely on electromagnetic wave for the molecular communications. Due to the nature of the chemical diffusion, the propagation speed is extremely slow, extremely low. The thing is that, here we're not arguing we should replace 5G networks with this kind of the diffusion-based molecular communications. Rather, do we have here? Here we propose this concept to have the quite different the applications, like the health monitoring or something like that. Also, here we have the different noise sources, and the encoded information is also quite different. Of course, the target application here, we just we don't deliver the voice or text or video contents using the molecular communications. That is a big difference between traditional stuff and the molecular stuff. So I know it's hard to believe this concept. This radically is possible, but what about in practice? To answer to this question, I have prepared a very short video clip, and let's watch this first. Can you guys see this and the video clip?
Yes.
All right. Okay. All right. Here, we have the Arduino, very cheap, the micro controller, and then we try to deliver the 6 alphabets YONSEI, like what's explained before. We have the controllable spray, and we have a fan, the backside, to have the some drift, the velocity, and then you can hear some sounds. Like when we have some sound, it means we release the certain amount of the molecules. So just by using very simple modulation that I explained before, we call that the concentration-based, simply on-off keying. And then we successfully received the messages. We can watch one more time. So the each alphabet can be encoded into the 5 bits information just by using ITA2, the standard. So YONSEI, since we have the how many? 6 alphabets. So we transmit total 30 to 35 bits, and the just by using some reliable detection algorithm, which will be explained later, and we successfully received the message. So surprisingly, we received the message, and this is the world's first test bed that does not have any RF technologies. So what did you learn from this video? So we also have several more test bed with the more advanced techniques, and you guys will see them maybe next week. So is it feasible? Yes, it's feasible. And where can it be applicable? Where we can use these concepts. So you may wonder, where we could use this approach. We here have the 3 representative applications. For free space applications, we could have the tactical, macro scale, or nanoscale robots that have the robustness against the eavesdrop. So which means we can use those kind of technologies for military communications, or for the individual the applications, as I already introduced, the health monitoring nano robots, or target drug delivery system could be some good examples. So biocompatibility is keywords for these applications. And for underwater application, officer sensing, reporting, or the leakage detection for like oil pipe may be quite useful. So throughout my lectures, I will mainly focus on the first and the second applications. There's the one guy, the West Go, from University of Warwick, and he recently moved to Cranfield University or some other university, and he has really big project for the underwater applications. And if you have any questions, I can just share that information maybe tomorrow or next week. So then, who first proposed the concept of molecular communications? I have Googled and found the article, entitled here. You can see my point here, right? Here, the new concepts of the molecular communication among neurons in 1979. I read that as well, but they were mainly dealing with purely the biological aspects of the real molecular communications, and they did not discuss communication protocols. In 2005, Tadashi Nakano, he is now with the Osaka University, and his colleagues published a paper entitled "The Molecular Communications for Nano Machines Using Intercellular Calcium Signaling." The small conference. And I believe this was one of the first papers on molecular communications. 3 years later, Professor Ian Arkwright from Georgia Tech, they published a magazine-type article in 2008. Since then, the research on this topic has exploded. Now we have the dedicated journals for this topic. One is IEEE Transactions on Molecular, Biological, and Multi-Scale Communications. And the other one is by the Elsevier and Nano Communication Networks. So, in the last decade, since 2010, and I think more than 1,000 papers have been published. I don't know, maybe a few thousand or 10,000 papers. All the papers can be classified into the mainly 3 categories: the communication engineering aspects, and the macro scale, nanoscale, and practical and experimental systems. For the communication engineering part, researchers have investigated channel models, modulation techniques, error correction codes, and simulation tools. So architecture and protocols and optimal design. The concepts were mainly based on classical communication theory. For macro scale areas, the information particles and channel and the propagation and transmitter receiver mechanisms and components have been studied. On the other side, more biological stuff was considered for the microscale networks like kinesin over the microtube and bacterial assisted propagation and so on. So more recently, the several groups, including my group, have tried to demonstrate their concept through the prototypes. Or the details can be found in the ComSurvey, the paper by Nariman and some colleagues. I am also a co-author of this paper. So all right, then next, let's talk about the diffusion, the dynamics. The Brownian motion. I think everybody heard about Brownian motion. The Brownian motion is the random motion of the particles suspended in a medium. Medium could be the liquid or a gas. So this pattern of the motion typically consists of the random fluctuation in a particle's position inside the fluid subdomain, followed by relocation to another subdomain. Each relocation is followed by the more fluctuation within the new closed volume. So this pattern describes a fluid at some equilibrium defined by a given temperature. Usually we assume the room temperature 25 degrees in Celsius. Within such a fluid, there exists no preferential direction of flow. More specifically, the flow's overall linear and angular momenta remain known over time. And this motion is named after the very famous botanist, the Robert Brown, who first described the phenomenon in 1827 while looking through the microscope at pollen of the plants. I think the plants, the Clackia perchella or something like that, that's immersed in water. After that, in 1905, almost 80 years later, the theoretical physicist Albert Einstein published a paper in 1905. It's a miracle year, where he modeled the motion of the pollen particles as being moved by the individual water molecules, making one of his first major scientific contribution. This explanation of the Brownian motion served as convincing evidence that, the atoms and molecules exist, and was further verified by the experimentally by Jean Ferrand in 1908. The Ferrand here. He also awarded the Nobel Prize in Physics in 1926 for his work on I forgot the name of the paper, discontinuous structure of matter or something like that. And the direction of the first atomic bombardment is constantly changing. And at the different times, the particle is hit more on one side than the another, leading to the seemingly random nature of the motion. But the main body interaction, the Brownian pattern, cannot be solved by a model accounting for every involved molecule. In consequence, the only probabilistic models applied to the molecular population that can be employed to describe this kind of some nature. The two such models of the statistical mechanics, thanks to Einstein and Smoluchowski, I think they are Russian, very famous physicists, are presented later. Another pure probabilistic class of models is the class of, the stochastic process model. And there exists a sequence of both the simpler and more complicated the stochastic process, which converts to Brownian motion. So in physics, more specifically, the kinetic theory of the gases, the Einstein relation, also known as the Wright-Sullivan relation, is a previously unexpected connection revealed independently by the William Sutherland in 1904 or 3, the Albert Einstein in 1905, and by Marian Smoluchowski in 1906 in their work on Brownian motion. You know, the more general form of the equation here is that the diffusion coefficient is mu kbt, and here mu is the mobility, and or sometimes the ratio of the particle's terminal drift velocity to an applied force. And you know, the Einstein did not consider explodes, but molecules may explode when the pushing forces like a drift velocity collide in the smaller scales, the observation. So he has the more general the assumption and observation, and he has the more accurate the expressions. So for the diffusion coefficient, there are two frequently used special forms of the relation. One is the electrical mobility equation for diffusion of the charged particles, and the other is, you know, the very famous the Stokes-Einstein equation for diffusion of the spherical particles through a liquid with a low Reynolds numbers. Don't worry about it. I mean, I will explain the what Reynolds number is later. So therefore, for lamina-dominated cases without explosion, and we can still use the Einstein model. So as I mentioned, the Brownian motion is the random motion of the particle. It's suspended in a medium that could be, you know, the liquid or gas. And I believe that we all learn this Brownian motion or diffusion equation in the engineering mathematics course during the undergrad studies. So this equation here and is the first order in time, and then the second order in space. That is quite famous heat transfer equation sometimes and diffusion equations. So there are two parts to the Einstein's theory. The first part consists in the formulation of the diffusion equation for Brownian particles, in which the diffusion coefficient is related to the mean squared displacement of the Brownian particle. In the meantime, the second part consists of in relating the diffusion coefficient to the measurable, the physical quantities. So you don't need to worry about the second part. In this way, the Einstein was able to determine the size of the atoms and how many atoms there are in a mole, or the molecular weights in grams of gas. So he theoretically calculated Avogadro's that number. And that number was really, really accurate. It has the same order, I believe, 10 to the 23 or something like that. So the first part of the Einstein argument was to determine how far a Brownian particle travels in a given time interval. The classical mechanics is unable to determine this distance because of the enormous number of the bombardments the Brownian particle will undergo. So roughly of the order of the 10 to the 14 collisions per second. Thus, Einstein was led to consider the collective motion of the Brownian particle. So we know that the solution of this diffusion equation, where is that here, is a Gaussian distribution. But this is true only for when we care about the distance. When you care about the time, like what we have in communication, things are different. So let's take a simple example here. Suppose we release a certain amount of the messenger molecules at x0 and t equals 0. And if you measure, and if we are interested in the location of the molecules, so we're gonna have the Gaussian distribution. However, if we are interested in the time, so we're gonna have inverse Gaussian distribution. Again, here, one of the simplest stochastic system is the Brownian particle in one dimension, just for simplicity. The system describes the motion of the particle, which moves stochastically in one-dimensional space with equal probability of moving to the left side or to the right side. Given that the Brownian motion is used as a tool to understand more complex phenomena, it is important to understand the probability of our first passage time of the Brownian particle of reaching some position distance from its the start point, the start location. This is done through the following means. The probability density function, PDF, for a particle in one-dimensional is found by solving the one-dimensional diffusion equation. This equation states that the position probability density diffused outward over time. It is analogous to say, suppose we have the cream in a cup of coffee. If the cream was all contained within some small location initially, after a long time, like 1 day or so, the cream has diffused throughout the entire drink evenly. Namely, we solve this equation given the initial condition. It can be shown that the one-dimensional PDF is, after some calculation, this is the one. So this means that the probability of finding the particle at xt is the Gaussian, and the width of the Gaussian is time dependent. There's a difference. So the first passage time density, FPTD, is the probability and the particle has the first reach the point, the xc. Here, subscript C denotes cliff, used in many texts. The exactly time t. Here, please note that this is not at some time during the interval up to t. Exactly the time t. This probability density is calculable from the survivor probability, which is more the common probability measure in statistics. It's quite popular terminology. They consider the observing boundary condition, and we can derive the PDF to satisfy this boundary condition. So it's hard to understand the single step here, but don't worry about that. I will share the all the papers that I used to make these slides. So here, the survival, the probability, and the probability that the particles remain in a position x smaller than xc for all times up to t is given by, this is the survival probability. But the relation between the survival probability and the FPTD is like that. The probability that a particle has reached the observation point between times and t, and suppose t plus delta t, and ftdt is st, the first one, minus st plus dt. If one uses the first order Taylor approximation, the definition of the FPTD follows the second equation here. Just by using the diffusion equation and integrating the explicit FPTD is the third one. This is the one I think that you can carefully take a look at. That is the inverse Gaussian distribution for the 1D space. Here, the variable is time. Variable is not a distance anymore. So this is the usually good for the communications because we fix the distance between the transmitter and receiver. We care about the arrival time because unless the receiver has any arrival the molecules, and we cannot detect the information. So by using the diffusion equation and this one, and we can also have some asymptotic the behavior. So if we assume that t is much larger than the certain constant here, And Ft is the proportional to the t to the minus 3 second with the a bit different exponent. So in early 1900s, there's no internet, there's no Google. So many similar studies were conducted simultaneously. The mathematician Louis Bachelier is also sometimes credited with being the first person to model the stochastic process, now called the Brownian motion, as part of his PhD thesis. That's the theory of the speculation. The bachelor's doctoral thesis, which introduced the first mathematical model of the Brownian motion, and it's used for valuing the stock options, was the first paper to use advanced mathematics in the study of the finance. Thus, therefore, the Bachelier is considered as the forefather of the mathematical finance and a pioneer in the study of the stochastic process. By the way, the Henri Poincaré, the famous mathematician, was his advisor. In 1908, Paul Langevin, I'm not quite sure that my pronunciation is correct or not, but Langevin published a paper entitled On the Theory of the Brownian Motion in American Journal of the Physics. And he was also the doctoral student of the Pierre Curie, and later is the lover of the Marie Curie. So I'm not quite sure if I should explain in detail here. Okay, the original Langevin equation described the Brownian motion, the apparently random movement of the particle, and here the degree of freedom of interest here is the velocity of the particle, and the force acting on the particle is written as a sum of the viscous force proportional to the particle's velocity. And he has considered the more general situations, but I guess you can simply remember the Einstein's equations for your research that is accurate enough for analyzing the molecular communications system. So far we have covered the very fundamentals of the diffusion dynamics, and I think that I can take some questions before moving. So from now on, let's focus on communication part. So the goal of the communication system, I guess we all know, is to transfer the information across space and time. To achieve this, a signal needs to be generated by a transmitter in accordance to be the information that is intended to be transformed to a receiver. The signal then propagates to a receiver where the intended information is encoded from the received signal. Therefore, any communication system can be broken down into three major components: the transmitter, the receiver, and the channel. This slide shows the block diagram, the representation of these three modules and their sub-modules. The channel is the environment in which the transmitter signal propagates from the sender to the receiver. In a traditional communication system, a channel is typically a wire, like of fiber optics or even cable, or free space for RF communications, where the transmitted signals are the electrical currents or electromagnetic waves, respectively, for those two different channel conditions. In molecular communication, the small particles called information particles act as chemical signals conveying the information. The information particles are typically a few nanometers to maybe a few micrometers maximum in size. The information particles could be biological compounds, like such as protein, or synthetic compounds, like gold nanoparticles that the many semiconductor engineers use. The channel in molecular communication is the liquid or gas environment where the tiny information particle can freely to propagate. In communication system, the channel may introduce noise into system, of course, as well, where the noise is any distortion that results in the degradation of the signal at the receiver. In radio-based, like the RF-based communication systems, the source of noise is typically the fading of the electromagnetic signals or diffraction, and the interference of the different electromagnetic waves. For example, like due to the multipass, and we have these several undesirable signal. So in the molecular communication, the sources of the noise can be like the random propagation noise and transmitter emission noise and receiver counting noise and environment noise, such as the degradation and or the reaction, and also the multiple transmitters. And when the transmitted signal arrives at the receiver must first demodulate and detect the channel symbols. The estimated signal, the channel symbols, after that, decoded using the channel decoder, where some of the error introduced by the transmitter, the channel, and the receiver may be corrected. We can still use the quite similar channel codec technologies here. Of course, we cannot use very high complexity Tupper code or LDPC code for tiny nanomachines, but there are some papers proposing the ultra low complexity, very simple but powerful channel coding solutions. The output of the channel decoder goes to the source decoder, where the receiver estimates what information the transmitter has sent. If this estimation is correct, then the communication session has been successful, the same as before. But the channel for the communications. In 1959, physicist Richard Feynman gave a lecture, really famous lecture, at the American Physical Society meeting in Caltech. And the title was his talk is "There is Plenty of Room at the Bottom." The goal of the talk was to inspire the scientists and the engineers there for finding a solution to the problem of manipulating and controlling things on a small scale. To motivate his vision of the never-ending limits of the miniaturization, he asked, why cannot we write the entire 24 volumes of Encyclopedia Britannica on the head of a pin? In 1959, it was very impressive. Over the past couple of decades, there has been considerable advancement in the field of nanotechnology, biotechnology, microrobotics, where the designing and engineering of the microscale or nanoscale devices begin to take the shape. So in order to achieve the complex goals, the cooperation of these devices is essential. And therefore, a microscale or nanoscale networks of the multiple micro nano devices must be formed and must be fabricated. This leads to a need for miniaturization of the current communication systems and poses a question similar to the one Feynman asked almost half a century ago. How much can we shrink a communication system? So we will begin to this question later. And here, let's focus on the channel first for the micro and nanoscale system. So molecular communication has the two main advantages over electromagnetic communication for nanonetwork. First, it is biocompatible, which means it could be used for medical application with ease. Second, it is energy efficient and has a very low heat dispersion. Therefore, the molecular communication becomes a more suitable solution for the nanonetworks. Of course, we have to, and evaluate fairly also with the EM solutions. But at this moment, I'd like to argue that molecular communication is better for the health monitoring or other stuff that we can use for the nanonetworks. So for microscale, the molecular communications, many different propagation schemes are possible for transmitting the information particles. They are here. Diffusion based propagation or flow assisted propagation, because we have the blood inside the pipe here. And active transport using molecular motors of the cytoskeletal the filament here, and bacterial assisted propagation, and kinetic molecular motors moving over immobilized microtubule tracks, and so on. So, right in these days, we have quite a lot of the researchers coming outside from the other area. So sometimes I got the recent papers from Department of Biology or Department of Chemistry for the IEEE transactions, the MBMC, that journal. So at this moment, we have quite various researchers in this area. And among all these possible channel scenarios, in these lectures, I will mainly deal with the diffusion-based channel. The parameters we should consider include the diffusion coefficient and direct velocity profile and bounded conditions and degradation effect by enzyme. Please note that here, we don't have the RF antennas anymore. I have added these antenna icons only for ease of the explanation. So it should be chemical transmitter and chemical receiver. And I'm not quite sure if you could see the details here, but this slide illustrates the channel environment on the left side and channel responses in a vein blood vessel on the right side. In each channel environment, the point transmitter emits the molecules, and a spherical observing receiver counts the number of the received molecules. The transmitter and the receiver are assumed to stick to the surface of the three-dimensional cylindrical tube. Each environment under consideration has different flow phenomena by the velocity, the profiles. I will explain more in detail later. So for the channel responses on the right side, we could also adopt the cylindrical tube channel as in a body network channel models. I will, of course, give the more details later. So the point here is that we could consider the more practical situations to analyze nano communication networks. By the way, how many minutes do I have more? What time should I close the lecture today?
So normally you have 90 minutes.
Okay.
But I think due to it depends also when your first part is over, right?
Okay, okay. 60, and I will...
not more than 90, let's say like this. So that would be another half an hour.
All right, all right.
Next, then if you quit earlier because also it's late for you, that's totally fine with us.
All right, all right. And then I will have maybe 5 to 6 more slides, and then we'll have the different topic, and then we can have the more technical discussions before moving to the second part, because we have some time tomorrow and the one more slot early next week, so I can control all the contents, and it's better to have the more interactive discussions first to share some of the big picture. So okay, here, this is the transmitter and receiver. As I mentioned, in nature, most of the receptor types to remove the information carrying molecules from the environment once they arrive at the receiver, which means the molecules contribute to the signal once in a short duration. So therefore, considering the absorption is necessary, since using concentration or the molecule distribution function as the channel transfer function implicitly assumes the receiver node does not affect the molecular communication system. So the most prior work, including Einstein's work and other famous guys' work, and they assumed the point transmitter and a point receiver to measure the characteristics of the random walk. So we also have the similar the assumptions in our communications. When we plot the radiation pattern for a certain antenna, we first plot some shape for isotropic point source, which is not practical, but we assume that one only for the comparison purposes. So to consider the more practical receiver, we derive the first hitting probability function in a 3D environment for a point TX and an absorbing spherical RX. It is still an open problem for channel characteristics for spherical TX and the spherical RX. So for the receiver and the reception process in diffusion-based molecular communication models, there are mainly two types of models. The passive and the active. Active meaning observing receivers. The former assumes the molecules are unaffected by the receiver, while the second one, later assumes the molecules are observed whenever they hit the receiver. In the passive receiver case, the molecules can pass through the receiver node surface multiple times without interaction. Therefore, the molecules are allowed to contribute to the received signal multiple times when the receiver is passive. For the absorbing receiver case, the molecules contribute to the received signal only once, and the molecules that hit the receiver are removed from the environment. And this process is modeled by the first passage process, and to model the received signal, and we focus on the time dependent, the first hitting the histogram. So for here, the active receivers, here the active part is the solid 9. Once we hit the surface, it just disappeared. But for the passive receiver, it reflects, and then it moves around the receiver. Then it can hit several times. So we could, recognize that some differences between two cases. Even for the active case, passive case, it's really not that simple to derive those equations, but that we can compare here the differences. And for an active receiver case, there is some additional parameter D here in a numerator, and the exponent for the parameter T is different one. Is the 1, and this is the 3. That's a big different one, and we can validate, we can confirm those two different analytical formulations with the particle-based the numerical simulations. So let's consider the more practical solution. Here in this DS subsection, I'm talking about communication unit. I mentioned the channel part, I mentioned the transmitter and receiver. So as in the RF communications, when you think about communication part, we also have the transmit radiation pattern or received radiation pattern. So similarly, so we have the different terminology though, but we have the similar stuff here. So let's consider the more practical solutions. It's not that feasible to have the point transmitter in practice, but we also assume this for the simplicity. So here we have the two system models of molecular communication with point and spherical transmitter cases. So this is the one for analyzing, but still there is no closed form expressions for channel characteristics for this configuration. This is still an open problem. In the spherical transmitter case on the right side, the molecules are reflected by the body of the transmitter. Here, when we release certain amount of molecules, it goes back to the surface of the transmitter. It is bounded by that surface and might be back to the surface again because we have the only random walk, random movement. So two example locations for the receiver nodes here are shown for both cases with the same distance d here. The distance should be the same for the fair comparison. So for the spherical transmitter case, that the receiver at here the 0 degree corresponds to the perfect alignment scenario. So in the molecular communication via diffusion system, simply molecular communication system, there is at least one transmitter and one transmitter and receiver pair in a fluid environment. So in general, the transmitter nodes are assumed to be points and receiver nodes spherical. So here, so let's remove the assumption of having a point source for the transmitter side. And instead, we consider the spherical transmitter which reflected emitted molecules like what I explained before. And the thing is that the number of the received molecules is expected to be higher for this case, right? Compared to the point source case. So this is analogous to a radiation pattern in RF communications. Just by controlling a size of the transmitter and the initial release energy. And then we can have so-called the chemical pattern, which also increases SNR at the receiver. What I mean is that here, if we have the bigger transmitter, and then we have the more reflections, and then there's the almost zero possibility or probability that we could measure or observe some molecules because the transmitter blocks almost everyone. In doing so, we can have the more molecules to that direction. That is like the radiation pattern to have the higher directional gain. So here we plot the number of the received molecules at the angle, suppose we have the alpha until time t. We also plot so-called half power pattern width, which is the directivity gain at each angle with respect to the point source. In RF communication, we also have the similar terminology, half power beam width. But here, since we do not have beam concept, and we name that half power the pattern width. So it is also defined as the angle that is to the half of the received molecules at perfect alignment case. So first observation here is that when we increase the transmitter node size and the half power pattern width narrows and the received power increases gradually due to the slide. This is kind of the guidance given by the transmitter node. So it can be clearly seen that having a spherical reflecting transmitter affects the received power. So we can also claim that for the spherical transmitter case, if the receiver node is placed between the -20° and 20°, which means if the receiver and the transmitter are well aligned, then the received power is higher for the given parameters. On the other hand, if we consider the reception on the backside of the transmitter, and we observe that the received power diminishes quickly. So, here we have nothing here backside. So we can consider these low power values as the interference leakage to other receivers on the backside of the transmitter. So, here, so far I introduced the transmit chemical pattern, but here, like the transmission chemical pattern, we could also utilize the receive chemical pattern. As we already noticed, one of the major and common challenges in molecular communication is the intersymbol interference, which is caused due to the late reception of some messenger molecules in the channel. We only have the random walk. So consequently, the many recent work has focused on the overcoming this issue, by the proposing either some noise modulation or equalization methods. Or we can also use the WebDM concept to mitigate intersymbol interference, even for the molecular communications. But we can also use the different types of molecules, but they usually require a significant amount of the additional computational complexity. So as the alternative solution, we model the received molecular signal for partially counting observing receiver. That is, the receiver observes all hitting molecules, but those counted are only the ones hitting at a specific site, only this area, not this area. And the thing is that how can we optimize that angle to achieve the lower the bit error rate? So, I'm sorry. So the modeling, the time-dependent, the received signal for this kind of system is an open issue and has the potential to enhance the communication system performance without any significant additional cost. So most of the received molecules are observed from the surface area facing toward to the transmitter side. So as the path, the backside of the receiver is longer, and the receptors on that side are more likely to receive the interference the molecules. Therefore, limiting the counting area to the front side with a limited surface area may enhance the signal quality. That is a basic concept of this idea. And as shown in this figure, the argument of the global maximum of some objective function and we defined the paper is very close to the argument of the global, the minimum of the bit error rates. So here, SID stands for the signal to interference difference that we define. Using this concept, using SID, the optimization problem achieving the lower bit error rate is written as a function of the angle alpha here to determine whether the receiver observes or neglects. From this result, we could confirm that a partially counting observing receiver demonstrates a significant improvement over the conventional fully observing one. So, quite simple. Just by controlling the angle, and we could reshape the sensitivity, and it's like received radiation pattern in RF communications. As I mentioned before, like the RF communications, so we do also have noise. It is also desired to investigate the performance degradation due to these noises. There have been quite few papers in this topic. I guess that's mainly that it's hard to have the real measurement data yet. So if you have any good idea, you could be a leader of this subdomain. So, in communication system, the channel may introduce noise into system where the noise is any distortion that results in degradation of the signal at the receiver. So, as I mentioned before, the sources of the noise for molecular communications are random propagation noise, transmitter emission noise, and maybe counting noise as well. Because at the receiver side, the receiver node should count how many molecules the guy receives. And for the detection algorithm, simply we can use the thresholding based one, like the on-off king that we used for like optical communication or direct communication. Then the threshold is very sensitive. So if we have some error or noise in counting the number of molecules, and it results in some performance degradation. So we should be very careful about with handling those noise as well. So far, I have cover the communications unit, and from here, I will introduce more about the channel model.